Hello everyone, welcome back to our course on zero-knowledge proof. I'm Yupeng Zhang, and today I'm going to talk about polynomial commitments based on bilinear pairing and discrete logarithm. Recall that from previous lectures, we've learned that a common recipe to build an efficient snark system is this general paradigm in two steps. We first design a proper interactive oracle proof, such as a polynomial IOP, and then we can combine it with a polynomial commitment to build an efficient snark for circuit evaluations. In the last lecture, Dan has taught about the Planck scheme, where we can reduce the computation of a general circuit to several proof gadgets, such as polynomial equality testing, product check, permutation check, and so on. Combining the Planck IOP with a univariate polynomial commitment, we will get an efficient snark for general circuits. Earlier in lecture 4, Justin talked about interactive proofs and showed how to check the circuit satisfiability using the classical sum check protocol. At the end of this protocol, the verifier has to evaluate a multivariate polynomial defined by the prover's witness at a single point. And this is again realized by a multivariate polynomial commitment scheme in order to get an efficient snark. So in today's lecture, I'm going to formally present the constructions of polynomial commitment schemes based on bilinear pairing and discrete logarithm. Combining them with the polynomial IOPs we learned before, we will eventually have the complete description of several efficient snark schemes. So to start, what is a polynomial commitment? It is again a protocol between a prover and a verifier for a family of polynomials. For example, univariate polynomials with degree less than or equal to d. And the prover has this polynomial in the family. And without sending it directly to the verifier, the prover can commit to this polynomial through a polynomial commitment. Later, the verifier can issue a query on the evaluation at this point u, and the prover replies with the value v and the proof pi, proving that v equals to the evaluation f of u, and at the same time, f belongs to this family of polynomials. More formally speaking, there are 4 algorithms of a polynomial commitment scheme: keygen, commit, eval, and verify. The keygen takes the description of this family of the polynomials and the security parameter and outputs a set of global parameters. It is also known as a public key or public parameters or common reference string, but in this lecture I'm just going to use GP to represent it. Then given GP and the polynomial, the prover can compute the commitment of this polynomial. And later at the evaluation point u, the prover can call this eval algorithm to output the evaluation v and the proof pi. And finally, the verifier can verify the correctness of this claim using GP, the commitment, u, v, and pi, and output either accept or reject. The correctness of a polynomial commitment says that if the prover is honest and follows all of these algorithms, then the verification always outputs accept. And I omit formal definition here. More interestingly, we want the scheme to be sound, meaning that the prover should not be able to lie about this evaluation. And here I'm showing the formal definition of a knowledge soundness. It says that for every polynomial time adversary, given the global parameters generated by keygen, if the adversary can output a valid commitment, evaluation, and proof that pass the verification with probability 1, then there must exist an efficient extractor that uses A so that it can extract a polynomial f, where f of u equals to v, and fx belongs to this family of polynomials with an overwhelming probability. So that is the formal definition of knowledge soundness of polynomial commitments. So in order to fully understand the construction of polynomial commitments, there will be 3 segments of this lecture. So first, I'm going to introduce some mathematical and cryptographic background on groups, discrete log, and bilinear pairing. After that, I'm going to present the classical construction of this KZG polynomial commitment using bilinear pairing, and also talk about its variants. Finally, in the last part, I will talk about polynomial commitment schemes without trusted setup, such as bullet proofs, and also highlight some other schemes based on discrete logarithm, such as hierarchs, Dory, and dark. So let's start with some background. The first thing I want to define is a group. A group is a set of elements and an operation star that satisfy these four properties. And I think it's actually easier to walk through these properties with a concrete example that everyone knows, like integers and their additions. As you can see here, closure means that given two elements in the integers, a and b, then a plus b should also be an integer. And this is clearly true for integers and their addition. Associativity says that computing the result of a plus b and n plus c should equal to a plus the result of b plus c. And this is also true for integers. And identity means that there exists an identity element such that e plus a equals to a plus e equals to a itself. And 0 is the identity element for integers under addition. And finally, for every element in this set, there exists an inverse such that a plus b equals to 0. Again, for integers, this is taking the negative of the number. So because of this, integers under addition satisfy all of these four properties, so it forms a group. And other groups that people are familiar with include rational numbers, real numbers, complex numbers, and so forth. However, group we use in cryptography are quite different. For example, a common group we use is positive integers modulo a prime number p under multiplication. And the set is 1, 2, 3, all the way to p minus 1. And this is a finite set. And you can check that it actually satisfies all these four properties and thus form a multiplicative group. Another common group we use is defined by elliptic curves, but I'm not going to go into details in this lecture. And I will mainly use this example of a multiplicative group modulo p in this lecture. So given the definition of a group, then for every group there exists the concept of a generator. So the generator is an element that can generate all elements in this group by taking all powers of this element, G. For example, taking the multiplicative group modulo the prime number 7, the elements include 1, 2, 3, 4, 5, 6, and then we can actually take 3 as an example as an element. You can see here that if you take all the powers of 3, and of course the computation always done modulo 7, you can see that it iterates through all possible elements, 3, 2, 6, 5, 4, 5, 1 in this group. So because of this, by the definition, 3 is a generator of this multiplicative group of Z7 star. By the way, there usually exist multiple generators, and they can be efficiently computed and sampled in practice. With this definition of a generator, then a group G has an alternative representation as the powers of the generator G. You can write it as G to the 1, G to the 2, all the way to G to the p minus 1. This is because by the definition of the generator, this set iterates through all possible elements. So this is essentially the same set of the group in a different order. Here, note that in this lecture, I'm using the multiplicative notation, where the operation of the group is multiplication, and exponentiation means repeating the multiplication multiple times. Recall that in the last lecture, Dan was using the additive notation, where the base operation is addition. Each of these two notations is convenient for different protocols and is actually good for you to understand both notations. But I will use the multiplicative one in this lecture. So because of this alternative way of defining the group, then we can formally define a problem called discrete logarithm. The problem is given an element y in this group, please find x such that a generator g to the power of x equals to y. This is well defined for every y because of this alternative representation, and the problem is analog to the logarithm computation in the continuous case, thus it is called discrete log. So then let's see an example on the multiplicative group mod 7. And so please tell me what is x such that 3 to the x equals to 4 mod 7. Can you compute it now? Actually, you can't figure it out immediately, and basically the naive solution is try out all possible x to see which one is true for this equation. And this suggests that this problem is actually hard to solve. And this is known as the famous discrete log assumption. The assumption says that this discrete log problem is computationally hard. And basically, the naive solution is try all possible elements in the group, which the complexity of which is proportional to the size of the group, and it's computationally hard if the size is exponentially large. And there are better algorithms in practice that improves the running time a little bit, but still it's considered not in polynomial time. And by the way, this discrete log assumption does not hold in all groups, but is believed to hold in certain groups that are used in cryptography. And also, quantum computers will actually solve this discrete log problem in polynomial time. Therefore, all protocols based on the discrete log assumption will not be post-quantum secure. Another popular assumption that is highly related to the discrete log assumption is called the Diffie-Hellman assumption. And here I'm presenting the version called computational Diffie-Hellman assumption. It says given g to the x and g to the y, you cannot compute g to the xy efficiently. And it's also a fundamental assumption in cryptography. And you can see here that clearly if you can solve the discrete log problem, then you can compute x from g to the x and y from g to the y, and then use them to compute g to the xy. So therefore, this assumption is stronger than the discrete log assumption. But still, it is believed to be hard in the groups we are using in cryptography. With these definitions, I'm ready to present the important building block we are going to use called bilinear pairing. So in a bilinear pairing, in addition to the group G and the generator G, we also have a target group called GT and an operation called pairing. We use E to denote it. The base group G and target group GT are both multiplicative groups of order P, and G is the generator of this base group G. And the rule for the pairing operation is that it takes two elements in the base group as input, P to the X and Q to the Y. And after the pairing, it gives you an element in the target group, which equals to E PQ to the power of XY. So basically, it's computing the product in the exponent of this equation. So again, to get familiar with it using an example, given g to the x and g to the y, the pairing of these two elements equals to egg to the power of xy. And by a similar rule, this also equals to the pairing between g to the xy and the generator g itself. So this gives you a way that given g to the x and g to the y, you can actually check if some element h is g to the xy or not without knowing x and y. So basically, this gives you a tool to verify the product relationship in the exponent of the computation, but not computing it. So note that using pairing, you cannot break the computational Diffie-Hellman assumption. You cannot compute g to the xy directly, but you can use pairing to check if someone gives you the result of g to the xy, whether it is true or not. And again, for your information, not all groups in which discrete log is hard are believed to support efficient computable pairing, but some groups are, especially those defined by elliptic curves. So a good example to get more familiar with this pairing operation is through this elegant design of a BLS signature. This was proposed by Benet, Lin, and Shaichang in 2001. So the key generation of this BLS signature is very simple. The private key is just a random element x, and the public key is g to the x. By the discrete log assumption, given g to the x, it is hard to figure out the x, the secret key. In order to sign a message, we are going to compute the hash of this message and then raise it to the power of x, where h is a cryptographic hash function that maps the message space to the base group. In order to verify the signature, note that everyone can actually compute h of m, that is a public hash function. But without knowing x, we cannot compute the hash of m raised to the power of x directly. So what can we do? Here comes the pairing operation. We can actually pair the h of m with g to the power of x, which is a public key. This is known by everyone. And then check if it is the same as the pairing of the signature and generator itself. If the signature is computed honestly as h of m to the power of x, then this verification will pass. So that's the correctness part of the BLS signature. For soundness, in the paper, it can be shown that if there exists an adversary that can forge signatures, then we can actually use the adversary to break the computational Diffie-Hellman assumption in this bilinear group. So therefore, this signature scheme is secure. So this shows you an example that utilizes the power of the pairing to check the product relationship in the exponent of this equation. With the background on the bilinear pairing, I'm ready to show you the construction of the KZG polynomial commitment scheme in the second segment of the lecture. The KZG polynomial commitment scheme was introduced by Kate, Zavaricha, and Goldberg in 2010, and the applications in the original paper include verifiable secret sharing and verifiable polynomial delegations. But in recent years, it has become a very important building block to construct efficient snark systems in practice. Recall that there are 4 algorithms for a polynomial commitment scheme. We have a key generation that generates a set of global parameters, and then the prover calls this commit algorithm to compute the commitment for a polynomial f. Later, for an evaluation point u, the prover calls the eval algorithm to compute evaluation together with the proof pi. And finally, the verifier calls the verify algorithm to verify the correctness of the evaluation. And we're going to go through the 4 algorithms of the KZG polynomial commitment scheme one by one. The scheme works on a bilinear group with a base group G, a target group GT, and a pairing operation E. And the basic version works for the family of univariate polynomials with degree less than or equal to d, where d is a publicly known parameter. First, in the key generation algorithm, we are going to sample a random number tau in this finite field mode P. And then we are going to use tau to compute this set of global parameters. In particular, we are going to raise g to the different powers of tau. We have g to the power of tau, g to the power of tau square, and so on all the way to g to the power of tau to the d. Note that the size of these global parameters is linear in the maximum degree of the polynomial we want to support. Intuitively speaking, since we are using a group in which discrete log problem is hard, no one should be able to compute tau given this set of global parameters. So in that sense, tau is hidden in the exponent of the generator G. After that, an important step of this key generation algorithm is that we have to completely delete this secret key tau. That is because, interestingly, in the remaining part of the KZG polynomial commitment scheme, we are not going to use this tau at all. It suffices to use the global parameters to commit and generate the proof and to verify the evaluation. And if anyone can have access to this secret key tau, then they can actually generate a fake proof to fool the verifier and to break the security of this polynomial commitment scheme. So it is very important to discard this tau after the key generation algorithm. And this step is called the trusted setup, because we have to trust this preprocessor to discard this toxic waste of tau after the execution. And in practice, this is not desirable for many applications because it is hard to find a trusted party to run this trusted setup. So given this set of global parameters, the way to commit to a polynomial is as follows. First, we are going to represent this polynomial in the form of the coefficients. We have f0 plus f1x plus f2x squared and so forth, all the way to fd x to the power of d. Then the commitment we are trying to compute is simply g to the power of f evaluated at the point tau. And turns out the prover can actually compute it without accessing tau directly. We can actually compute it using the global parameters only. That is because if we just expand the expression of f of tau, we get g to the power of f0 plus f1 tau plus f2 tau squared and so on. And by the rules of exponentiation, it equals to g raised to the power of f0 times g to the tau raised to the power of f1 times g to the tau squared raised to the power of f2, and so on and so forth. And this is because basically the addition in the exponent is equivalent to multiplications in the base level, and multiplications in the exponent is equivalent to exponentiations in the base level. So in this way, we can compute the commitment using this equation. And note that each of these elements in the parentheses is actually from the global parameters directly. So in this way, the prover can actually raise each value in the global parameters to the corresponding degree defined by the coefficient of the polynomial and get this commitment without using tau directly. So that's how we commit to a polynomial. And note the size of this commitment is only one element in the base group of the bilinear group. So after that, let's see how can we generate a proof for evaluation of this polynomial f at the point u. The most important key idea of this KZG polynomial commitment is actually based on this polynomial equation, where for any polynomial f, fx minus f of u can always be expressed as the product of two polynomials x minus u times another polynomial q of x, where the degree of qx is d minus 1. And it's actually not hard to see this relationship because u is clearly a root of this polynomial fx minus f of u. This equals to 0 at the point u. And because of this fact, then the polynomial fx minus fu can always be decomposed as x minus u times q of x. And there are other ways to prove the correctness of this equation, for example, using Taylor's expansion. So with this polynomial equation, then the idea of a KZG polynomial commitment is for the prover to compute this polynomial q of x, and then generate a proof pi equals to g raised to the power of q evaluated at point tau. Again, this can be computed using the global parameters only, without accessing this tau. And the proof size is only one element in the base group of the bilinear group. Finally, how can we verify the correctness of this evaluation? Then the idea of this verification is to check this polynomial equation at this secret point tau. In particular, what we are trying to check is g raised to the power of f tau minus f of u should equal to g to the power of tau minus u times q of tau. And this is basically replicating this polynomial equation in the exponent at the point tau, substituting the variable x. And here I'm listing what will happen if the prover is honest. Basically, the prover is going to commit to g to the f of tau, and the proof is g to the q of tau, and this evaluation v is f of u. So given all of these values, we almost have all the information about this equation to check. So on the left-hand side, we have g to the f of tau given by the prover, and we have g to the f of u, again given by the prover as the evaluation. On the right-hand side, the verifier knows the evaluation point u. This is the public information. And we have a g to the tau in the global parameters. And the prover returns g to the q of tau as the proof. But unfortunately, we cannot compute g to the tau minus u times q of tau directly. This is because the verifier is only given g to the tau minus u and g to the q of tau as the proof. And by the computational Diffie-Hellman assumption, it is actually hard to compute g to the power of tau minus u times q of tau, given these two values. So what can we do? Well, the solution is to use bilinear pairing. Recall that pairing gives you a way to check the product relationship in the exponent of the equation instead of computing it. So with pairing, instead of computing g to the tau minus u times q of tau, we are going to check the correctness of this computation. In particular, we're going to pair the commitment divided by g to the power of the evaluation v with the generator. And on the right-hand side, we're going to check whether this is equal to the pairing of g to the tau minus u and the proof itself. And to see the correctness of this verification, if we substitute these commitments and proof by the correct evaluations provided by the honest prover, we can see that the left-hand side equals to each g to the power of f of tau minus f of u because of the rule of the pairing equation. And on the right-hand side, if pi is honestly computed, it should equal to g to the power of q of tau. And then by the rule of bilinear pairing, the right-hand side equals to EGG to the power of tau minus u times Q of tau. It's basically computing the product in the exponent. And finally, because of this equation, if the prover is honest, this equation, pairing equation, should hold. EGG to the power of f tau minus f of u should equal to EGG to the power of tau minus u times Q of tau. This is essentially checking this equation at the secret point tau. And that completes the description of this entire KZG polynomial commitment scheme. Finally, to put it back to this slide showing the interactions between the prover and verifier, in the key generation algorithm, we are going to generate the global parameters as g to the tau all the way to g to the tau to the d. And this is the trusted setup step. And then for a polynomial f of x, the prover can commit to it using only the global parameters and compute g to the f of tau as a commitment. Later, for an evaluation point u, the prover computes this polynomial equation, fx minus f of u equals to x minus u times q of x. After figuring out q of x, the prover computes this proof pi as g to the power of q tau. And finally, the verifier checks this polynomial equation in the exponent using the pairing operation. And that is complete description of the KZG polynomial commitment. Now we've explained the correctness of the KZG polynomial commitment scheme. Namely, if the prover is honest, then the correct evaluation, the proof, can always pass the verification because of the polynomial equation. But what about soundness? Why can the prover return a wrong evaluation and a fake proof and still pass the verification? Well, the soundness of the scheme is actually based on so-called Q-strong bilinear Diffie-Hellman assumption. The assumption states that given a bilinear group and the global parameters, g to the tau, g to the tau square, all the way to g to the tau to d, an adversary cannot compute this value EGG to the power of 1 over tau minus u for any constant u. And this is actually a variant of the discrete log assumption and the Diffie-Hellman assumption. From the name, you can actually tell that there is a rigorous reduction from this assumption to the computational Diffie-Hellman assumption, which means that this assumption is strictly stronger than the computational Diffie-Hellman assumption, but still we believe that this assumption holds in the bilinear groups we use in cryptography. So with this assumption, I'm going to show you the formal security proof of the KZG polynomial commitment scheme. And this slide will be quite technical, but I'm going to go through it slowly, step by step. And I also think that it's really an elegant security proof and it's a good place to show you a formal proof in cryptography here. So a common approach to prove security in cryptography is by contradiction. In the first step, we suppose that there exists an adversary that can return a wrong answer V star that is not equal to f of u, and the fake proof, but still pass the verification. Then by the equation of the verification, we have the pairing of the commitment divided by g to the V star, and the generator g should equal to g to the power of tau minus u paired with the fake proof pi star. This is directly from the equation we check in the verification. The next, I'm going to cheat a little bit and write this commitment as g to the power of f of tau for some polynomial f known by the adversary. And this is actually a big assumption, because for just a randomly generated number as a commitment, you cannot always write it as g to the f for some f known by the adversary. And we need a so-called knowledge assumption to really make it happen. I'm going to explain it in detail later in the lecture. So if we're good with this writing this commitment as the g to the power of f of tau, then the next step is the key idea of this security proof. Because this V star is different from the real evaluation f of u, we are going to subtract f of u from this value in the exponent and then add it back. the purpose of doing this is that now in the exponent we have f tau minus f of u, which is the correct evaluation of this polynomial, plus a difference term, which we define as delta equals to f of u minus v star. And note that this delta is non-zero because v star is not equal to f of u, because the prover is cheating. So then, now we have the correct evaluation f of tau minus f of u in the exponent. This can be decomposed as tau minus u times q of tau for the correct q in the exponent. Again, by the polynomial equation I introduced earlier in the lecture. And then by the rule of the bilinear pairing, we can try to extract these elements in the exponent and put it outside of the pairing. So the left-hand side equals to egg to the power of tau minus u times q of tau plus this delta. And on the right-hand side, the eg is equals to eg pi star raised to the power of tau minus u. Then from this equation, we can see that the two terms in the left-hand side and on the right-hand side, they both have a common factor tau minus u. So we can actually combine these two terms together. By dividing this leading term in the front on both sides, we get egg to the power of delta equals to this eg pi star divided by egg to the power of q tau, together raised to the power of tau minus u, because they both have a common factor of tau minus u. Then once we reach this step, you can roughly get the idea of how to break the Q-strong bilinear Diffie-Hellman assumption, right? So from both sides, we can actually raise them to the power of tau minus u inverse. And note that here, I'm not saying that anyone knows this secret value tau minus u and can compute inverse. I'm merely stating the fact that if we do that, we have the following equation. And in the following equation, on the left-hand side, we have egg to the power of delta divided by tau minus u. This is almost the same as the problem of the Q-strong bilinear Diffie-Hellman assumption. We are trying to compute this value. On the right-hand side, it equals to this value inside the parentheses. And note that the adversary can actually compute the right-hand side with the global parameters only. That is because this eg pi star is known by the attacker because he literally generated the fake proof. And this egg to the power of q of tau is also known by the adversary because q of tau is the correct proof, and you can't prevent the adversary from computing the correct proof. So the adversary knows both of these values and compute the right-hand side, which means that the adversary can use this contradiction, use this fake proof to break the Q-strong bilinear Diffie-Hellman assumption. But then we assume that this assumption is computationally hard, which means that it is a contradiction. The first step of this v star not equal to f of u should not happen. So that completes the entire security proof of the KZG polynomial commitment scheme. And if you can't follow the entire derivation, note that the key idea of this security proof is to decompose this fake value v star into the correct value f of u and a difference delta. And then we can actually extract the common factor of tau minus u in the exponent. So that is the most clever step of this security proof, in my opinion. So after that, we have actually a remaining part that is not solved yet. So because in the security proof, I actually made an assumption. And so when we see this commitment f, in the next step, I actually write it as g to the power of f of tau for some f known by the prover, known by the adversary. And this is actually a very big assumption. If the prover just generates a random value and call it the commitment f, how can you make sure that the prover actually knows this polynomial f locally? And this is actually hard to check. And this requires an additional assumption called knowledge of exponent assumption. So this key idea of this assumption is saying that for this global parameters for the KZG polynomial commitment, we are going to sample another secret value alpha and compute g to the alpha, g to the alpha tau, g to the alpha tau square, and so forth, all the way to g to the alpha tau to the power of d. Basically, we are raising each of the element in this global parameters to another power of alpha. And we are going to include both as the new global parameters. So now for every commitment g to the power of f tau, using the second set of global parameters, we can also ask the prover to compute g to the alpha times f of tau. And this is actually easy to do because we are just raising the corresponding element in the second set of the global parameters to the same coefficients of the polynomial f. So there is actually a one-to-one relationship between these two sets of global parameters. So after that, in the verification, we are going to check an additional pairing equation. So this equation is essentially checking the relationship between these two components of the commitment. We are going to do the pairing of the commitment, the first commitment, with g to the alpha, and then we are going to check it against the pairing between this commitment prime with the generator g. And again, if this com prime is computed honestly, then you can always pass this verification because it is the product equation in the exponent, and the left-hand side should equal to the right-hand side. And the assumption says that as long as you can pass this verification, there must exist an efficient extractor E that can extract a polynomial f such that the commitment equals to g to the power of f of tau. So this assumption directly solves the problem we were facing in the security proof. Given the commitment f, we don't know how to express it as g to the power of f tau, then by this assumption, if you perform an additional commitment com prime and an additional check using pairing, then there exists an extractor to extract g to the f of tau. So that is the knowledge assumption. With the knowledge assumption, we can actually solve this problem and get a real polynomial commitment scheme that satisfies knowledge soundness. So basically, in the key generation algorithm, we are going to generate two sets of public parameters, g to the power of tau, tau square, and tau to d, and g to the alpha, g to the alpha tau, g to the alpha tau square, and so forth. And for each commitment, it consists of two parts, g to the f of tau and g to the alpha f of tau. And to verify the correctness of evaluation, in addition to this pairing equation to check the polynomial equation, we also check that the pairing of com and g to the alpha equals to the pairing of com prime and the generator g. And by the knowledge assumption, in the very first step of the security proof, we can extract f such that the commitment equals to g to the power of f tau by the knowledge assumption. And that solves the problem of the security proof and gives you the final complete proof of the knowledge soundness. But then a problem of this knowledge soundness assumption is that it actually introduces an overhead in the commitment size and the verifier time. So now the commitment becomes two elements in the base group, and the verifier becomes two pairing equations to check. So it basically doubles the cost of this scheme. So in order to further improve this part, we can also prove the security in a model called the generic group model, GGM. So in GGM, informally speaking, the adversary is only given an oracle to compute the group operations. What it means that given a set of global parameters, the adversary can only compute their linear combinations in order to get another group element in the base group. There is no other way for the adversary to, for example, sample a random point and it happens to be another group element in the base group. Because of this model, we can actually use the GGM to replace the knowledge of exponent assumption and reduce the commitment size to one element and also the verifier time to one pairing equation to check. And this GGM is, again, a stronger model to work with, but is also believed to be reasonable because it captures all known attacks against the discrete log assumptions or Diffie-Hellman assumptions and the family. So that is why it is reasonable to use this to prove security in our case. And here is really an informal description of this GGM model. And please see the book by Dan and Victor for more details about the GGM model. So with all of that, finally, we end up with this KZG polynomial commitment scheme that is correct and the knowledge sound in the GGM model. And so to remind you again, we have these global parameters, and the prover commits to the polynomial as g to the power of f tau. And in order to prove an evaluation, we compute this quotient polynomial fx minus f of u divided by x minus u. And the proof is g to the power of q of tau, and the verifier checks it using a pairing equation. So finally, let's look at the properties of this KGG polynomial commitment scheme. So in the key generation algorithm, as we discussed, it requires a trusted setup. Someone has to pick this secret key tau, generate the global parameters, and remove this secret key tau completely. Otherwise, the security will be broken. And the commit takes order of d group exponentiations, computing to compute g to the power of f tau given the global parameters. And the size of the commitment is constant. It's only one group element in the base group. And the evaluation algorithm, the complexity of that is, again, order of d group exponentiations to compute g to the power of q of tau. And note that this polynomial q of x can be computed efficiently in linear time using just a simple long division. You don't have to use complicated polynomial divisions to do that. And the proof size is only one group element, order of one, and the verifier time is only one pairing equation to check. So that is why the KZG polynomial commitment is actually very efficient in practice with very small proof size and fast verifier time. But the only drawback is that it requires a trusted setup in the key generation algorithm. So another thing I want to mention is that in order to somehow relax this trusted setup assumption in practice, there is a process called ceremony. The goal of the ceremony is to have a distributed generation of the global parameters so that no one can actually reconstruct this trapdoor tau if at least one of the participants is honest and discards their secret. So let's see how can we do that. Well, the idea is very simple because of this nice structure of the global parameters. Recall that the global parameters is g raised to the different powers of tau. And we just call running global parameters generated by one party as g1, g2, all the way to gd. So then, if we receive these global parameters from another party, there is a way to introduce an additional part of the randomness called S and update this GP prime into a new set of global parameters. And the update is very simple. We are going to raise each element of this existing global parameters, G1, G2, and GD, to the corresponding powers of S. We'll compute G1 to the S, G2 to the S squared, all the way to GD to the S to the D. And if you just write down this equation formally, you can see that if GP is honestly computed, then this set of global parameters becomes g to the tau s, g to the tau s together square, and then all the way to g to the tau s together to the power of d. Which means that this new set of global parameters is actually equivalent to generating it using the secret tau times s from beginning. So this gives you a sense that if everyone's honest, then they can still form the correct generation of the global parameters using the product of all the secrets from all the parties. So finally, there are some additional steps to check that this GP prime is indeed correctly generated. in case that someone is malicious, we don't want them to ruin this entire global parameters. And there are two steps to check the correctness. So first of all, the contributor has to generate a proof proving that he or she knows S such that G1 prime equals to G1 to the power of S. Indeed, you are introducing some valid secret S from G1 to G1 prime instead of discarding this existing global parameters and generate GP prime from scratch. And this one can be done efficiently using, for example, a Sigma protocol. And another check we need to do is that after this computation, GP prime should have the form of consecutive powers of this generator raised to this new secret. And this can actually be checked efficiently using pairing. There's a simple check. We can actually do the pairing between Gi prime and G1 prime, and that should equal to Gi plus 1 prime and G for I equals to 0 all the way to D minus 1. And this shows that after the update, we still have a valid global parameters with this relationship. And also another thing we need to pay attention to is that we can't just remove the secret and change it to 0. So in order to prevent that, we have to check that G1 prime is not equal to 0. And this nice way of doing the ceremony was actually introduced in this paper in 2022. So that completes the discussion of the KZG polynomial commitment scheme. As we've seen so far, the KZG polynomial commitment has this simple and nice algebraic structure, and that's why it has led to many variants in the literature, and I'm going to discuss some of these variants next. The first extension is to the multivariate case, and the scheme was proposed by Papaventhal, Shi, and Tamasia in the paper in 2013. And here I'm showing you an example of a multivariate polynomial with k variables, and it basically can be expressed as the summation of all these monomials generated by these variables times the corresponding coefficients. And the key idea to build a multivariate polynomial commitment scheme is based on this polynomial equation. So for every multivariate polynomial, fx1 to xk minus fu1 to uk, the evaluation at this point, can always be expressed as the summation of x minus I minus ui times qix from I equals to 1 all the way to k. And here qix is again a multivariate polynomial. It's actually not straightforward to prove this equation, but I refer you to the original paper for a formal proof of this equation. And based on this polynomial equation, then in the key generation, instead of sampling one secret key tau, we are going to sample k secret keys tau 1 and all the way to tau k. And basically each tau is representing the one variable in this multivariate polynomial. Then we are going to compute the global parameters as g raised to all possible monomials generated by tau 1 all the way to tau k. And for example, as Justin discussed in lecture 4, for multilinear polynomials, there are in total 2 to the power of k monomials generated by all the variables. Then with this public parameter, the commitment is very straightforward. We are still computing g to the power of f tau, where tau now is a vector, tau 1 to tau k. And again, this can be computed using the global parameters only. The prover is raising each element of the global parameters to the corresponding coefficient of the polynomial and multiply them together to get the commitment. Next, in order to compute the proof, the prover is going to evaluate this polynomial at this point u1 to uk and invoke this equation to compute qix for all I. Then the proof consists of multiple elements. Pi I equals to g to the power of qi evaluated at the point tau here, for I equals to 1 all the way to k. And finally, to verify the correctness of this evaluation, we are again checking this equation in the exponent using bilinear pairing. On the left-hand side is exactly the same as the univariate case. We are computing the pairing between the commitment divided by g to the v with the generator itself. On the right-hand side, we have multiple pairings. So the verifier is computing the pairing between g to the power of tau I minus ui and pi I, and then multiply all of them together from I equals to 1 all the way to k. And if you do the derivation, this is essentially checking this equation at point tau I in the exponent. And for the similar reason, this scheme is correct and can be proved sound under the same assumptions. And in terms of efficiency, the commitment and the evaluation has the same complexity as before. Assuming that the n is the total size of this polynomial, then both of them are order of n group exponentiations. But the scheme does introduce an overhead on the proof size and the verifier time. So now the proof size becomes order of k, which is order of log n, for example, for a multilinear polynomial. And the same applies to the verifier time. So this is the scheme for multivariate polynomial commitment. The second extension I want to introduce is a way to achieve zero knowledge. And I refer you to see lecture 1 for the formal definition of zero knowledge. In the case of a polynomial commitment, essentially zero knowledge is saying that there exists a simulator. Without knowing the polynomial, the simulator can actually simulate the view of the verifier and generate this proof. And that is indistinguishable from real execution with the polynomial. And turns out this plain KZG is not zero knowledge. And the simple way to see it is that this commitment equals to g to the power of f tau is actually deterministic. Although you cannot reconstruct f of tau directly from the commitment, you can actually do some testing for this polynomial. For example, we can assume that the polynomial a zero polynomial. Well, if that is true, then g to the f of tau must be equal to g to the power of 0, which equals to 1. And you can actually check whether the commitment is 1 or not. And that tells you whether the polynomial is all 0 or not. And in general, you can make any hypothesis about whether a polynomial is of certain form, and then compute the corresponding commitment and check that if it's the same as a real commitment. So in this way, you can actually learn some information about this secret polynomial. So that is why this scheme is not zero knowledge. And the key reason is that this commitment is deterministic and can be computed by anyone. So the key idea to make it zero knowledge is to mask both the commitment and the proof with some randomizers. And here I'm showing you a scheme from my paper with my co-authors in 2018. So the key idea of this scheme is that instead of committing to g to the power of f of tau, we are going to add a randomizer term, that is r times eta, where r is a random number chosen by the prover, and eta is actually another secret key sampled by the preprocessor in the trusted setup. And of course, we also need to include g to the eta in the public parameters, but I'll omit this step in this informal description. And then to generate the proof, instead of doing the regular decomposition, fx minus f of u, we're going to do a randomized decomposition. You see here that on the left-hand side, we have an additional term, r times y, which is actually from this randomizer of the commitment. And here we are replacing eta with a variable y. And on the right-hand side, instead of doing x minus u times q of x, we are going to do x minus u times q of x plus r prime times y, where r prime is another randomizer sampled by the prover to mask this proof. And then if you expand this multiplication, we will see that this is the remaining term, and all of them have this common factor y. So we can write it as y times r minus r prime times x minus u. With this decomposition, we can actually generate the proof pi consisting of two elements. The first element is g to the power of q tau plus r prime eta, which is essentially evaluating this polynomial inside the first parenthesis at point tau substituting x and the eta substituting y. And the second element is g to the power of r minus r prime times tau minus u, and essentially from the second polynomial in the parentheses. And then we can check this relationship of the randomized decomposition with the pairing equation to check the product in the exponent. And this is how we achieve zero knowledge for the KZG polynomial commitment scheme. And another interesting thing to think about is that actually this scheme is almost equivalent to generalizing the univariate KZG polynomial commitment scheme to the bivariate case. We're essentially adding an additional variable y so that we can actually use this term to randomize both the commitment and the proof. And for a correct evaluation of f of u, we're essentially evaluating this bivariate polynomial at the point u, 0, where 0 is for the variable y. And in this way, we can achieve zero knowledge. So finally, the last variant I want to introduce is this batch opening. So the first version, I want to start from a single polynomial, where there is one polynomial held by the prover f, and the prover wants to convince the verifier that the evaluation of f at multiple points, u1 all the way to um, for m that is smaller than degree d. Because if it's larger than d, then you can reconstruct the polynomial in the first place. So the key idea to generate a short proof for these multiple evaluations is that we can actually extrapolate the evaluations fu1, fu2, all the way to fum to get a polynomial h of x. The property of this h of x is that hu1 should equal to fu1, hu2 should equal to fu2, and so on and so forth, and hum should equal to fum. And there exists a unique polynomial of hx of degree m with such a property, with a leading coefficient 1. So with such a polynomial h of x, then we have a new equation here. Fx minus h of x equals to the product of x minus ui for I equals to 1 to m times the quotient polynomial qx. Why is that? Again, we can check the roots of this polynomial on the left-hand side. If you evaluate this polynomial at u1, then because of the property of h of x, fu1 equals to hu1. So the left-hand side is 0 at point u1. For a similar reason, it is also 0 at u2, u3, all the way to um. So because of that, u1, u2, and u3 and all the way to um are all roots of this polynomial fx minus h of x. And because of that, it can always be decomposed as this product times the quotient polynomial q of x. So then we are going to compute the proof pi as g to the power of q tau as in the regular case with one opening. And note that this is only a single element in the base group for multiple evaluations. Finally, we can check this polynomial equation at point tau using the pairing again. So on the left-hand side, we are going to compute the pairing between the commitment divided by g to the h of tau and the generator itself. And the verifier is able to compute this g to the h of tau using the global parameters. On the right-hand side, we are going to compute the pairing between g to the power of the product of tau minus ui. Again, the verifier can compute it using the polynomial interpolation and global parameters. And then we're going to do the pairing between this one and the pi itself. And if the prover is honest, then this equation should hold because of this polynomial relationship. And we can prove the soundness in a similar way and reduce it to the Q-strong bilinear Diffie-Hellman assumption. So in this way, for multiple evaluations, m evaluations, the proof is still a single element. But note that the verifier time is actually order of m, grows linearly in the number of evaluations. And finally, in the extended version, which was actually left as a homework in the previous lecture by Dan, there exists a batch opening protocol for multiple evaluations, multiple polynomials and multiple evaluations. So now in the most general case, the prover commits to multiple polynomials, fix for I equals to n, for I belongs to n, the set n, and then the prover wants to prove that fi uij equals to vij for J belongs to the set of M. And the key idea is kind of similar to a single polynomial case. For every polynomial fi, we are going to extrapolate fi u1, fi u2, and I'm missing an index here, fi um, to get hix for I in N. Then, for the similar reason, we have a polynomial equation for every polynomial. Fix minus hix equals to the product of x minus uim times qix. So we are going to have a qix for each polynomial fi. And then we can combine all of these qix via a random linear combination and compute g to the power of that polynomial, which is only a single element in the proof. And then the verifier can actually reproduce all of these equations in the exponent using the public parameters, and then check this equation using bilinear pairing. So in this way, we can actually batch the multiple evaluations of multiple polynomials into a single proof. So that's all the variants I want to discuss about the KZG polynomial commitment scheme. So going all the way back to the general purpose snarks, with these variants of KZG polynomial commitments, we can actually construct snarks based on these polynomial IOPs. For example, using the Planck system, we can combine this Planck polynomial IOP with the univariate KZG polynomial commit scheme to get a snark for general circuits. And this is exactly the construction proposed by the Planck paper. And in terms of interactive proofs, there are actually several papers proposing these constructions. So we can actually combine a sum check protocol or a variant called the GKR protocol for layered arithmetic circuits with the multivariate version of the KZG polynomial commitment. And that leads to an efficient snark for the computation of circuits. And this idea was used in the systems called VSQL and later in Libra in these two papers. So that completes the discussion of the polynomial commitment scheme based on bilinear pairing. And in the next segment, I'm going to talk about other polynomial commitment schemes based on discrete logarithm. Welcome back to the last segment of this lecture. In this segment, I'm going to talk about polynomial commitment scheme without trusted setup based on discrete logarithm. Recall that the KZG polynomial commitment scheme has very impressive performance in practice. Both commitment and the proof size are only order of 1. It's one group element each, and verifier time is only one pairing equation. But the main drawback of this polynomial commitment scheme is that it requires a trusted setup to generate global parameters. And of course, the ceremony process relaxes this trust a little bit and is actually good for many applications in practice. But still, this trusted setup is a fundamental problem to solve. So in recent years, there has been a main focus to construct efficient, transparent zero-knowledge proof schemes without trusted setup. And in this lecture, I'm going to talk about the scheme based on Boole proofs, which was proposed by Boodle et al. In 2016 and later refined by Bunz et al. In 2018. And in the original Boole proof paper, they proposed an inner product argument and has a special protocol for range proofs and also can be generalized to proofs for a general arithmetic circuit. But here I'm just going to rephrase this Boole proof protocol as a polynomial commitment, because it can still show the key idea of this Boole proof reduction, but it will significantly simplify the protocol. So in this scheme, the key generation is actually very simple. We're just going to sample the global parameters as d+1 random elements in this group. Without there's no trapdoor or secret key in this setup process, so that is why we call it a transparent setup. And note that the size of this global parameter in the construction of Boole proofs is still linear in the degree of the polynomial. With these global parameters, the commitment of the scheme is also very simple. So again, given a polynomial fx equals to f0 plus f1x plus f2x squared, and so on all the way to fd times x to the d, the commitment is simply g0 to f0 times g1 to f1 times g2 to f2, and all the way to gd to fd. So basically, we are still raising each element of the global parameters to the corresponding coefficient of this polynomial, and then multiply them together to get a constant size commitment. And for those who are familiar with the Peterson commitment, you can see this is actually the standard commitment scheme for the vector version of the Peterson commitment. And here I'm omitting the random term of the Peterson commitment, but it is actually not hard to just add a term h to the r at the end, and all the protocols should follow. So with this commitment, I'm going to first describe the high-level idea of this bulletproof reduction. So when the verifier picks an evaluation point u, the prover replies with this v as the evaluation of this polynomial at point u. And here I'm using an example of a degree 3 polynomial, which equals to f0 plus f1x plus f2x squared plus f3x to the 3. And clearly the evaluation is equal to this equation if the prover is honest. And the key idea of this bulletproof reduction is to actually reduce this claim of evaluation v at point u for the polynomial inside this commitment to a new claim about a new polynomial of only half of the size. So through a reduction, we want to reduce this original polynomial of degree 3 to a new polynomial of degree only 1 with two coefficients, f0 prime plus f1 prime x. And then we can somehow compute the commitment of this new polynomial as comp prime with some new basis g0 prime to f0 prime times g1 prime to f1 prime, and also a new claim about the evaluation v prime for the new polynomial at point u. And if you can do this, then the verifier will receive a new instance of this polynomial commitment for a polynomial of degree only half. Then we can just keep doing this recursively to reduce the new instance to another polynomial of degree only d over 4 and d over 8, and all the way to a constant degree polynomial. And finally, if we don't care about the zero knowledge for the time being, then in the last round, the prover can just send this constant size polynomial to the verifier directly, and the verifier opens the polynomial and checks that the evaluation of the last round is indeed true. And that completes the entire reduction and guarantees that the original evaluation of this v for this polynomial of degree 3 is actually correct. So that is the high-level idea of this bulletproof. But the main challenge of this reduction is how can we go from this original polynomial to a new polynomial of half of the size? We have to check the relationship between these two polynomials. You can't let the prover just to commit randomly to a new commitment without any relationship before, and then commit to a new evaluation v prime. Then the prover can just cheat and lie about the original evaluation because there's no relationship between v and v prime and com prime. So the major challenge and the protocol we are going to see next is how can we establish such a connection between the old instance and the new instance. So here I'm listing the global parameters as G0, G1, G2, and G3. And a common way to reduce the polynomial to half of the size is to actually decompose it to two parts. And the way I'm doing here is we're going to have a left part of the polynomial and the right part of the polynomial. And here you can see that I'm defining VL as f0 plus f1u, which is from the first half of the coefficients of the original polynomial fx. And similarly, we have VR equals to f2 plus f3u, which is from the second half of the polynomial. Note that I'm restricting the degree of both polynomials as only one, half of the original polynomial. So with these two values, it's not hard to see that the original evaluation v should equal to VL plus VR times u squared. So that gives you a way to check the correctness of this VL and VR. After that, another quite common approach to reduce the original polynomial to a new polynomial of only half of the size is through random linear combination. So now we have two parts of the polynomial, first half and second half. Then the verifier picks a random number r and sends it to the prover, and the prover is going to combine these two polynomials by multiplying r times the first half plus the second half. And the result of that is this new polynomial of only two elements. In this new polynomial, f0 prime simply equals to r times f0 plus f2, and f1 prime equals to r times f1 plus f3. So in this way, we reduce the original polynomial of degree 3 to a new polynomial of degree 1 that is only of half of the size. Then with this new reduction, it's not hard to see that the evaluation of this new polynomial at point u should equal to r times VL plus VR. And this is the new claim V prime the verifier is trying to check. So in this way, I show you a simple approach to reduce this polynomial to a new polynomial of only half of the size, and at the same time, the verifier has already checked the claim about the relationship between the new evaluation V prime and the old evaluation V through these two parts of VL and VR. So the only remaining challenge is to generate the commitment of this new polynomial. But turns out this step is quite challenging, because given this new polynomial, you can't let the prover just to compute the same Peterson's commitment using the same basis. For example, if you ask the prover to commit G0 to this first term and G1 to the second term, there is no way for the verifier to check that this new commitment is indeed computed from the vectors in this old commitment COMF. That is because now we have a transparent setup. We don't know the relationship between these different bases. And we can't compute computations in exponent across these different bases. So in order to address this issue, here's the clever design of this bulletproof protocol. So in addition to this VL and VR, in the same round, we are going to ask the prover to send two more commitments. And the first one is G2 to F0 times G3 to F1, and the second one G0 to F2 times G1 to F3. So intuitively speaking, this is the commitment to the first half of the polynomial, and this is commitment to the second half of the polynomial. That's why I name it L and R. But interestingly, the bases are different. We are using G2 and G3 to commit to the first half, and G0 and G1 to commit to the second half. So it's kind of a cross term for this to compute these commitments. We are using the second half of the basis to commit to the first half of the polynomial, and then we use the first half of the basis to commit to the second half of the polynomial. So that is L and R. Again, both of them are only one element in the group. So with L and R, turns out the verifier is able to reduce this old commitment COMF to a new commitment for this new polynomial. And how can she do that? Through this magical equation. The verifier is going to compute com prime as L to the power of this random R times the original commitment times R to the power of small r inverse. And with that, we claim that this commitment is actually for this new polynomial under a new global parameters. Why is that? Now I'm going to explain this magical computation in this slide. So here I'm listing the information received from the prover if the prover is honest. So the original commitment is this G0 to F0, G1 to F1, and so forth. And the left part is the cross term for the first half, and R is the cross term commitment for the second half. And the verifier is computing this com prime as L to the R times the old commitment times R to the small r inverse. So what is this computation? Well, then let's just expand it term by term. So first, let's see what's happening for this base G0. So in this equation, the second term com has this a term G0 to F0. So we're going to write it here. And R contains the term G0 to F2. And then we raise it to the power of small r inverse. So that gives us R inverse times F2. And there's no term inside this commitment L with base G0. So the result of this computation gives you G0 to F0 plus R inverse times F2 on top of the base of G0. Similarly, let's take a look at G2. From the commitment L, there's a G2 to the power of F0. And when we raise it to the power of small r, that gives G2 to R times F0. And from the old commitment, we have G2 to F2. And we don't have anything with the base G2 in the commitment R. So in sum, that gives us G2 to the power of R times F0 plus F2. And then we can do the derivation again for the bases G1 and G3. And again, G1, you have this G1 F1 from the commitment, and a G1 F3 from the R part, and raise it to small r inverse. So we have G1 F1 plus R inverse times F3. And finally, for G3, you have this G3 F3 from the commitment, and G3 to the F1 times R from the L part of the commitment. So all I'm saying is that it looks complicated to expand everything and figure it out, but there's no magical math involved. You just do it step by step for every basis, and you end up with this equation as the new commitment com prime. So then with that, the interesting observation is we can actually extract a common factor from the exponent of G0 and G2. And this common factor happens to be R times F0 plus F2. Clearly, you have this factor from in the exponent of G2. And so you end up with G2 in the parentheses. From the exponent of G0, if you extract this R inverse out, then the remaining term equals to R times F0 plus F2. That is why it also has a common factor R times F0 plus F2, and the remaining term in the parentheses is G0 raised to the power of R inverse. Similarly, we can do the same thing for the base of G1 and G3. And the second part of the new commitment equals to G1 to the power of R inverse times G3, together raised to the power of R times F1 plus F3. And recall that this is exactly the new polynomial we're trying to reduce to. Right? The new polynomial contains two coefficients. The first coefficient is exactly this R F0 plus F2, and second coefficient is R times F1 plus F3. So that is saying, after this computation, the verifier ends up with a new commitment. And this is, again, the same as the Peterson commitment. And the exponent is actually from the new polynomial. And the bases are from these two numbers in the parentheses. So we have to update these global parameters as G0 to the R inverse times G2, and G1 to the R inverse times G3, and combine them together. So in this way, we have a new global parameters, or new set of bases of only half of the size. And this com prime is exactly the commitment of this new polynomial using this new basis. So that solves the problem of establishing a connection from the old commitment to a new commitment with the help of these two values L and R. So going back to the original picture, that completes the description of one step of this reduction. So in each round, the prover can actually send VL, VR as the evaluations of first half and second half, and L and R as the cross-term commitments of the first half and second half. And verifier can update the commitment as this equation and derive the new basis as this equation, and compute the new claim of evaluation V prime as R times VL plus VR. So in this way, they can reduce the original polynomial and evaluation to a new polynomial and evaluation of only half of the size. And note here that another point I want to highlight is someone may be familiar with, for example, the standard FFT reduction, which actually decompose the polynomial as the odd terms, odd coefficients, and even coefficients. And I believe it's actually still working. You can actually decompose it as odd and even instead of the left part and right part. And the same protocol should still follow for this polynomial commitment based on bullet proofs. So with this protocol of the reduction, here we can actually generalize it to a polynomial of any degree d. So with the commitment of that polynomial, the job on the prover side is to compute this L, R, VL, and VR in each round. And then the prover receives the randomness from the verifier and reduces polynomial f to f prime of degree only d over 2. And here, to be precise, I'm actually assuming that the degree d plus 1 should be a power of 2. So after reduction, the degree should be d minus 1 over 2 or something like that. But this is not that important and just a corner case. And after that, the prover should update the basis from the original global parameters GP to GP prime using the equation I explained before. On the verifier side, the verifier receives two new claims, VL and VR. First, she has to check that they're consistent with the original claim, the evaluation V. And then the verifier generates this R randomly and updates commitment as this equation, updates the global parameters, and also updates the claim of the evaluation V prime as R times VL plus VR. And after that, they're going to do a recursion for log d times to further reduce the degree to d over 4, d over 8, and all the way to a constant polynomial. And to complete this entire protocol, in the last round, the prover simply sends this constant size polynomial to the verifier checks it against the commitment, checks that the evaluation in the last round is correct, which completes the entire reduction of this bulletproof, and guarantees that the original evaluation of this polynomial of degree d is actually correct. So that is the complete description of this polynomial commitment scheme based on bulletproofs. And here I won't go into the details of the soundness proof of this bulletproofs, but roughly speaking, you're using this random linear combinations to actually combine two claims about the left part and the right part into one claim of only half of the size, and refer you to the original paper for more details about the security proof. So finally, let's take a look at the properties of these bulletproofs. So in the key generation, there's no trapdoor or toxic waste. The setup is transparent, and the size of the global parameters is linear in the degree of the polynomial. So this is solves the problem of the KZG polynomial commitment. To commit to a polynomial, it also takes order of d group exponentiations, and the commitment is gain of size constant, one element in the group. And to generate the proof, it takes only order of d group exponentiations because it is a recursive reduction, and every time you cut the size of the polynomial to half, so in total, the complexity remains linear in the degree of the polynomial. And the version I described before is actually interactive between the prover and verifier, and you can actually make it non-interactive via the Fier-Shamir transformation. And in addition, the proof size is only order of log d, because in every round, the prover is only sending a constant number of elements to the verifier. Remember, there's a L, R, and VL, and VR, 4 elements in total in the version I'm describing. And finally, one of the main drawbacks of this protocol based on bulletproof is its verifier time. The verifier time is actually linear in the degree of this polynomial. And that is because, recall, in the description of this protocol, the verifier has also to update these global parameters by combining two bases into one using this random number R. And the complexity of this step is actually linear, which is the same as the complexity of the prover. So that is why the verifier time is actually quite slow in practice using this version of the polynomial commitment based on Boolean proofs. So in order to further improve the properties of the Boolean proofs, there has been other polynomial commitment schemes based on discrete logarithm in the literature. And I don't have time to go into details of these protocols, but here I'm just going to highlight the key improvements and the key ideas in these schemes. So the first scheme I want to mention is this hierarchy proposed by Wabi et al. In 2018. So in this paper, they propose another polynomial commitment scheme that improves the verifier time from linear to only square root d. And the key idea is to represent the coefficients of this polynomial as a 2D matrix. Then you can actually commit to this matrix row-wise and then do a reduction column-wise to get the final answer of the polynomial evaluation. And with this approach, the proof size and the verifier time are only linear in one dimension of the matrix. So in this way, we can achieve a proof size of a square root d and the verifier time of square root d. And also in the paper, there is actually a flexible way to choose these parameters. For example, the proof size can be further reduced to the nth root of d, with the cost of verifier increasing to d to the power of 1 minus 1 over n. So essentially, the product of these two has to be linear in d. So that is the polynomial commitment in the hierarchy paper. Another very important paper for polynomial commitment is called Dory, proposed by Lee in 2021. And this is a very nice improvement over the polynomial commitment scheme based on Boolean proofs. And the key contribution is to further improve the verifier time to only order of log d, without any asymptotic overhead on other parts. And the key idea of this Dory paper is to delegate the verifier's computation to the prover side. Recall that the verifier has to update this basis to generate a new set of global parameters by combining two elements in the old global parameters. And this is a very well-structured computation. You always take two elements from the global parameters that are publicly known and well-structured and combine them with using the random numbers chosen by the verifier. And using the approach called inner pairing product arguments proposed by this paper, Dory is able to delegate this computation of the verifier to the prover side, and the time to verify this step of computation is reduced to only order of log d. So with this approach, the verifier time is sublinear in the polynomial commitment. Another improvement to highlight is the protocol also improves the prover time to only order of square root d exponentiations, but the time to evaluate this polynomial remains order of d. So still, asymptotically, the prover time is a linear number of field operations. And this improvement also, concretely speaking, this improves the prover time significantly in practice. But for the purpose of constructing efficient zero-knowledge proof schemes, it really depends on your protocol. For some protocols, for example, the Planck protocol we covered in the previous lecture, the prover has to commit to a polynomial defined by the witness, and then later open it at some random point chosen by the verifier. And because of that, the prover time of the zero-knowledge proof scheme includes both the commitment and the prover time of the polynomial commitment. So in that sense, the addition of these two steps still remain linear number of exponentiations using the Dory construction. Finally, the last paper I want to mention is this dark paper by Boons, Fish, and Spieniek in 2020. So this paper also achieves a strictly order of a log d proof size and verifier time. And in fact, the scheme I described for polynomial commitment based on Boolean proofs in the previous slides is actually inspired by the construction in this paper. So this is also a very important paper in the literature. And the key idea is also delegating some of the verifier's computation with linear time to the prover side using some prior protocols. And the primitive, the cryptographic primitive this paper works on is this a group of unknown order. So finally, to summarize this entire lecture, so in this lecture, we've talked about polynomial commitment schemes based on bilinear pairing and discrete logarithm. And in the first part, we studied this classical design of the KZG polynomial commitment scheme. And this scheme has a trusted setup, but has a very impressive performance in practice. Both the proof size and the commitments are only one group of elements, and the verifier is constant time, a single pairing equation. And in order to remove this trusted setup and achieve a transparent setup, we have a sequence of works based on variants of discrete log problems in different groups. So the bulletproofs removes the trusted setup and achieves the logarithm proof size. And it is purely based on the discrete log assumption. But unfortunately, the verifier time is linear in the degree of the polynomial. Later, this is improved by the hierarchy construction with the cost of an increase on the proof size to square root d. And finally, we have two papers that achieves both logarithm proof size and logarithm verifier time without any trusted setup. The Doria paper is based on the bilinear pairing operation for the inner pairing product argument, and the dark scheme is based on the group of unknown order. So that is everything I want to talk about in this lecture. Thank you for listening.